All right, everybody, welcome back. So today we are going to do your exam 3 from last year, 2024. So there are a few changes this semester, and we'll talk about what those are when we get there. But for now, let's just jump straight in. So of course, you want to read all the directions and circle your answer choices in the first page. So this first question is asking, what is the highest boiling point? So I would underline this here, and then I would put off to the side. So boiling point, this is based off of hydrogen bonding. So if a compound can hydrogen bond, then the boiling point goes up as H bonds go up. So then you have to know what engages in H bonds. So you can put off to the side here, F, O, and N. So you can think of it like the hydrogens like to have fun. So that tells you if there's a H bound to F, O, or N, then you will have hydrogen bonding. So let's look through these. We can see in the first one, there are no H's bonded to the atom, so that won't be the answer. Second one, we do see that, so we'll put a check here. Third one, we see the oxygen, but we don't see any H's on it. So that's how we're gonna knock this out. Same thing here, we see oxygen, but we don't see hydrogens, so we'll knock this out as well. And in this one, we don't see oxygens. So the answer to this is going to be this. Okay, so jumping to the next question, it asks, circle the strongest acid. So for this, when you see the word acid, you want to go ahead and note that they're asking about the stability of the conjugate base. So the easiest way to do this is you just remove the hydrogen and put a minus. And then you can compare all of these structures. So a good test-taking strategy is if you see two answer choices that are very, very similar, the odds are one of them is going to be correct. So in this case, we have a benzene and a benzene. And then these are all just alkyl groups. So what you need to know about benzene specifically is that it is a withdrawing group. So essentially, when this minus charge is here, let me switch to a pen. So when you have a minus charge here, like this can resonate here, which can then open the benzene ring. So this is not the most stable of actions, but technically it is more stable than if you were to, let's say, push this here, because then this has 5 bonds. So that's just not allowed. So for that reason, we can say anything without a benzene is the wrong answer. So this is wrong, and this is wrong. And that's simply just due to the resonance. So we can write off to the side here. Resonance / withdrawing. Okay, so now it gets a little tricky when you're comparing this compound here to this compound here. So what you need to imagine is if you could resonate the lone pair more, let's do that right here. So if you can resonate this lone pair more, that's more stable. So in this case, if we move this here, then we can move this here. So if we move this double bond here, then we can move this lone pair here. Yeah. And then similarly, we can just go all around the ring. So we can move this here, here, here. And there's a ton of resonance there. Now the thing is, but also don't show it like that. You're gonna want to show it going from atom to atom. So you'll put a lone pair here, and then you can push that later. But the major key factor here is NO2. It looks like this. So you have a nitrogen bonded to an oxygen, bonded to the ring. So if we redraw this here, let's just scratch out these two O's here, and we'll draw them in. So it looks like this. This is plus, and this one is minus. So what you have to know about this is when the resonance makes its way around the ring. So when this comes here, and this comes here, and then from here, it'll go here, which will push this here. You can actually go ahead and push this here and push this here. So all that to say, this structure here has increased resonance relative to this one. So that's why the most acidic is going to be this structure right here. And that's simply due to its resonance. So just be comfortable with the idea that you can resonate into this ring and then you can also resonate out. Yeah. Okay. The next question asks, circle the compound which has the highest, or which has the metal in the highest oxidation state. So we're looking for something with metals. So first of all, this is water. This is not a metal. So we will cross this out. This is not a metal. And then what else is not a metal here? So the other groups look fine. Now this here, you can essentially do this two ways. You can look at increased bonds to oxygen, which is what I would do. So CrO3 versus OSO4. This has a 4, this has a 3, so I'll knock out this. KCN, it does not have 4 oxygens, it has 1 nitrogen, so I'll knock this out. Now here and here we see 2 O4s, so you need to ask yourself, back to Gen Chem, how do you do oxidation states? And the answer to that is you give the oxygen -2, so this is -8, because -2 times 4 equals -8. Then you have a K, which always has a +1 oxidation state. So that leaves the Mn, since this is neutral, it needs to be -8 plus 1, which is -7. So for this structure to be neutral, the magnesium Mn must be +7. Now in this structure here, we have O4. So we're going to do 4 times -2 equals -8. Now notice there's no potassium. There's no additional ion. So that means that the OSO4 has to balance the -8. So it should have a +8. So we can write here, the OS is +8. So when you're comparing +7 to +8, the +8 is the higher oxidation state. So that'll be this one. Okay. Now this one here says circle the only compound which produces a tertiary alcohol when reacting with the Grignard. So he said you guys don't need to worry about Grignard and alcohol, so we will skip this. And then circle the approximate pKa value of phenol. So this is one you just have to know. Phenol's pKa value is around 10. So that's the first page done there. Looks a little messy, but hopefully yours is cleaner. So now page 2 says, provide the missing conditions or reaction steps for the 6 reactions outlined below. Show all the steps, but you don't need to show the mechanism. Okay. Now this is going to be a little bit interesting, just because of the fact that he said you don't need to worry about Grignards reacting to form alcohols. So to save you guys time, this one will form an alcohol, this will form an alcohol, this will form an alcohol. This one, we'll do this one. And then this obviously forms an alcohol here. Okay, so here we have 2 boxes that we can fill in. So the first thing you should know about a Grignard is this is a very strong nucleophile. It's a very strong base. So you should also know that bases, these attack acidic hydrogens rapidly, particularly strong bases. So in this structure on the left here, we see we have an OH. OH, this is regarded as a strong acid. Oh, let's not call it a strong acid. We'll call this a weak acid. Just because of the fact that it does result in O-, which is decently stable. But ethanol is not the most acidic compound. It's just a weak acid. Something, if you want an example of a strong acid, you would see like H3O+, H2SO4, all the strong acids, HCl, HBr, etc. But anytime you see like a H2O, that's a weak acid. Methanol, ethanol, etc. These are all weak acids. That being said, it still has an acidic proton right here. So how this reacts is basically the Grignard. We'll move a step back here. Whenever you're looking at a Grignard, you can almost ignore this whole piece here, and you can just say this is a minus. So Grignard really is saying that there is a carbon minus, and this is like a counter ion. Now, how chemically correct that is, I'm not sure. But for the sake of taking these exams and passing them, you can call this a carbon minus. So you can imagine a carbon minus reacting with a proton, specifically this in the OH. I'll show you the mechanism, but you don't need to know it. It will just grab the OH, the H, and kick the bond there. So this will essentially just form the same compound, but now you don't have the Grignard. You have now attached the H here. So you don't need to show the H though. It's just kind of understood that you protonated it. So this is essentially a wasted Grignard, because you basically did nothing. You just protonated it, where normally you would use the Grignard to attach something. That being said, it's not the end of the world. You basically formed a new compound, so good job. Okay, now on this bottom one here, we need to figure out how can we form this ketone structure. And from the looks of it, it's an alcohol reaction. So you're gonna make an alcohol and then oxidize it, but you don't need to worry about that. So these, all the red X's, the X's indicate alcohol reactions. And you don't need to know that, so don't worry. Okay, now this part, naming, there's just a few rules to follow. So hopefully you guys remember the way to number a compound. So we'll go through this first one together. This has two options to start. We can go in green or we can go in red. So if we go in red, we hit 1, 2. If you go in green, you hit 1, 2. So green is better because you get a substituent at 2, whereas in red, you don't get that substituent until 3. So that's how you know you want to start on the right side. So we're going to say 1, 2, 3, 3, 4. Then you just want to label your substituents. So we see we have a 2-methyl. We know that our parent chain is a butane. And then we know there's 2 alcohols. There's a 1,4-diol. So to put this all together, there's a few ways to do it, but I think the easiest would be 2-methyl. And then you can say butane. And then -1,4. Actually, you want to put the numbers before. So you can say 2-methyl -1,4 butane-diol. Yeah. And another alternative that is acceptable, I think you can say 2-methyl butane di 1,4 all. But don't do this, just in case. So you're gonna want to do this. This is perfect. Okay, this next one, we see we have a ring. So we're gonna be including something like cyclo, but let's go ahead and number this. So you can start here or here. Of course, you want to give 1 to the substituent. So this is 1, 2, 3, 4. Now we see on, well, first we can label the parent. So this is a cyclobutane because it's a 4-carbon ring. And then we can also see we have a 1,3-diol. And then what's key here is since you have 2 groups that are the same, so we could look at the hydrogens or we can look at the OHs and compare these to each other. So since they are cis, you can say this is cis. So to put it all together, you would just say cis 1, 3 cyclobutanediol. Cool. Okay. And then on this last one, you have a few ways you can number this. So you can say 1, 2, 3, 4, or you can say 1, 2, 3, 4, 5, or even in light blue, you can say 1, 2, 3, 4, 5. So the reason that we go with the green numbering scheme here is because not only does it give the highest priority group the lowest number, it also gives the second substituent on the lowest number. So remember, you want to have the longest parent chain, then you also want to give your highest priority group the lowest number possible if possible. So we'd say this is 1, 2, 3, 4, 5, 6, 7. So this is a cycloheptene because there's a double bond here, so be careful. So we'll say this is cyclohept, and then it is a 4-ene. So we know that for now. Then we also know there's an alcohol at 1. So we would say 1-ol. And then we see a 2-methyl. Okay. So the way I would go about this is you can put the 2-methyl in the front. So a 2-methyl cyclohept 4-ene 1-ol. So that's pretty much it for the naming. The biggest thing is knowing that the alcohol is the highest priority group that you know so far. Okay, now this question, the key is the question is a little bit funky. So I'm gonna adjust this. So this double bond should be here. So it should look like this. So now we're wondering, why do we not form the Zaitsev? So it's saying, how can you explain the fact that the trans structure yields the non-Zaitsev, meaning the less sub product? So we need to figure out why. So if you remember in lecture what we said, the biggest thing for elimination, so for E1 or E2, well actually let's be specific. For E2, you need the leaving group and the hydrogen in something we called anti-periplanar fashion. So this just means that the H in leaving group must be anti. Now in this case, what we see here is the hydrogen and the bromine are cis. They're not, they're cis, they're not trans. So since they're not on the opposite positions, meaning that one of them is on this is a dash and this is also a dash, you can't eliminate here. You would need one of them to be on a wedge. That way they're sort of anti to each other. So for your explanation, and wow, this is worth 60 points, all you need to say is, we'll write it in green here. So since H and Br shown are not anti, elimination cannot form Zaitsev product. And then what I would do is I would number this as 1, arbitrarily of course, 2, 3, you can write here arbitrary numbering for reference. So we can make this since H on carbon 1 and bromine on carbon 2 shown are not anti, elimination cannot form the Zaitsev product, but H on carbon 3 is anti to the bromine, so elimination proceeds there. So there are two H's here on this carbon here. There's one on a wedge like this, and there's also one on a dash like this. So this one and this can eliminate to make this. So that's why. So if you ever are fully lost, remember, just write this down. You'll get like 30 points. Yeah. Okay, that's it for that. Now for this synthesis, you do unfortunately use a Grignard. So we will skip this. Uses Grignard to make alcohol, which is something you are not expected to do. So we'll skip this. And then you have this last page here. So this page is just talking about write the missing products or reactions for the so this should say reactants. For the reaction shown below, make sure to include stereochemistry. Okay, so we will be careful there, but do not write mechanism. Okay, so let's go through these and just give you what you need to know. So this right here, for the first one, is hopefully you recognize. This is tert butoxide. So hopefully you guys remember in lecture we said this, in the case of this exam, is E2 indicator. And that's because it is a strong base, but super bulky. So ask yourself, if this was not bulky, what other reaction type could this do? So it could do SN2. But the thing is, this is so large that it cannot fit here. This is just way too big, unfortunately. So that's why this is just going to do E2. So all we have to do is draw the elimination product. Now the pHs here, these are phenyl groups, which basically are benzene. So you can't really grab a proton off of this, but you can grab it from here. So you don't need to show the mechanism, but I will show you just for your sanity. So this base will grab the proton, which I'll put a double bond here and kick off this. So your product is going to look like this. You still have your phenyl. You still have this one as well, but not your double bond. Okay. Now we'll go down to this one. So here we see we have a secondary carbon. So I would write that down. So this is secondary, which doesn't really tell you anything about SN1, E1, SN2, E2. But it's always good to note that. Then we can see what we're reacting with. So we see NaCN. So this is really Na plus, C triple bond, N minus. Now this is a strong base. So we can say this is a strong base. It's also a strong nucleophile. Okay, now ask yourself, is this small enough to do substitution? Okay, and also note the solvent. This is in DMF. So DMF, this actually is a solvent for, hopefully you recognize this, it's a solvent for SN2. But if you don't remember that, it's okay. So look at the size of C triple bond N compared to something like what we saw up here, tert butoxide. It's pretty small, so this can actually fit in the backside of the structure. So you don't need to show the mechanism, but I will show you again. So this lone pair here will go backside attack, kick off the bromine. So you might be inclined to now draw the structure like this. But note, there's one thing special about SN2, which I'm sure you caught me already. We're going to invert the stereochem. So be careful, he pointed that out. So there's not going to be a wedge, it's going to be a dash, like that. Okay, cool. Now this third one here, you see CrO3. So this is an oxidizing agent. So this turns secondary alcohols into ketones. So all that's going to do is going to make the alcohol into a ketone. What that looks like is this. There you go. Okay. Now NaBH4, this is a reducing agent. this takes ketones to alcohols. So what you should know about this is that here we do not see any ketone. You should also know this takes aldehydes to alcohols. But in this case, we already see an alcohol here. So this is already an alcohol. So can we reduce an alcohol to an alcohol? No. So there is no reaction. That would be kind of backwards, right? You reduce an alcohol to an alcohol. Whose time are we wasting here? Okay. Anyways, moving forward. So we see on the next one, we have... excuse me. Okay. So on the next one, we see we're looking for reactants now. So we need to know, what does a reagent do? So Br2 and heat, you should know that this adds a bromine. So this adds a bromine to most subcarbon of alkane. Mechanism-wise, don't worry about it too much. But we see here that the bromine got added here. So all we need to do in our structure before this is just not have a bromine. You can draw it like this, or you can draw it like this. This is a more conventional style, so I'll draw it like this. Okay. On this next one, this one is pretty interesting. This one is pretty cool. So we see here, in our product, we have 2 double bonds, which is, okay, cool. Now we see here NBS. We know this NBS adds a bromine allylic to alkene. So allylic just means that if there is an alkene here, you can add it here or here. Yeah, what the heck? I don't know why it's doing that. Okay, you can add it here or here. The 2 positions, not on the double bond. This is horribly wrong, but the 2 adjacent positions. So here or here. Okay. So keep that in mind. We know that it only adds bromines allylic to the double bond. And then also we see here this huge, large, massive structure, also known as tert-butoxide. Okay, your mind should now be signaling. Whenever you see tert-butoxide, you're doing E2. Okay, so now what we can imagine is we are going to first step, we're going to add a bromine. Then the second step, we're going to eliminate it. So in our original structure, all we need to do is keep a double bond. Let me draw that a little better. We can keep this one because we know NBS will add a bromine here. And then we know the tert-butoxide will eliminate it and put the double bond here. So that's kind of the thought process there. Now this one here, of course, you're making an alcohol with the Grignard. So we're going to skip this for now. And then this last one, so what is NABH4? Let's write it out again. This is a reducing agent. And it takes aldehyde plus ketone all the way to alcohol. So wherever you see the alcohol here, we need to just make it a ketone. So it's going to look like this. Like that. And that's it. So hopefully you guys enjoyed this short video. I know we skipped a lot of questions. That's just due to the nature of the way that he wanted to talk about Grignards. So since he didn't want to test you guys with alcohols on Grignards, you don't need to concern yourself with that, which is honestly a good thing. So best of luck on your exams on Friday. And then I might post another video for synthesis. But all the synthesis that I've seen use Grignards. So I might have to do something interesting with that. But we'll see. Yeah, make sure you like and subscribe for sure. Help me retire. But yeah, good luck, good luck, good luck.